Hi there guys, Mr. Pope from Grammar School for Boys, and in the eighth session of when we're talking about geometry and vectors, I wanted to look at some more advanced matrix algebra. Now, if you've been following the channel, I know I'm slightly behind on videos, about 3 or 4 days, so hopefully I'll have brought that down to 3 videos by the time I get this and the next one down. But you'll probably be looking and thinking, hold on a minute, why not conic sections, what we were promised next? And the reason for that is I kind of wanted to tidy up vectors and matrices down first before moving on to conic sections. And I also felt that conic sections you need to know a little bit more about hyperbolic functions to truly get your teeth into it. So advanced matrix algebra, eigenvalues, eigenvectors, that kind of thing is what I wanted to look at today. So a couple of things. First of all, I want to talk about this idea of an eigenvalue and their associated eigenvectors. Okay, now I don't speak German, and to be honest, my grasp of the German language isn't that great, but I'm pretty sure that Eigen is German for of its own. Let me just Google that. I'm pretty sure it's kind of, it's like an intrinsic thing. Translate German. It's kind of like, you know, if something is intrinsically linked to something. Yeah, Eigen just means own. So when I'm talking about eigenvalue, I'm talking about the value of its own, and the eigenvectors are the vectors of their own of a particular matrix transformation. Its own. Almost think of it as like a characteristic. It's like a key trait of a matrix. So what do I mean by that? Well, suppose, and by the way, if you want some really beautiful animations, then I suggest you go to 3 Blue, 1 Brown's Essence of Algebra course when they talk about eigenvectors and eigenvalues. But essentially what's going on is if I've got a matrix A and I'm multiplying it by a column vector x, so let's say this matrix A is a 2 by 2, let's say A, B, C, D, and let's say x bar is some x and y, then this is going to be some scalar multiple lambda times x bar, which is just xy. Now this is really important because what this is saying is that for every matrix, whether it's a 2 by 2, 3 by 3, 4 by 4 and so on, and let's clarify, A has to be a square matrix. So this is an n by n matrix. Then what we say is that lambda is the eigenvalue, okay, and x bar in this case, well, that would be the corresponding eigenvector. Okay, if we find a vector such that by multiplying a matrix by it, that's the same as just multiplying that vector by a scalar, then we say that's an eigenvector. Geometrically, what's going on is suppose, let's take the 2-dimensional case because it's easier to draw. Let's suppose I've got several vectors. Let's say I've got a vector looking like this. Let's call this x1. Let's say I've got another vector over here. Let's say this is x2, and then let's say from the origin going down there like that, I've got x3. Now suppose I apply some transformation. So let's suppose I apply a transformation A to this coordinate system. Then let's suppose that x1, let's get rid of this x1 bit. Oh no, let's get rid of this x1 bit. Mate, come on. Let's say x1 after this transformation changes direction a bit and gets a little bit shorter. So now it's looking like this. So x1 prime, if you like, after the transformation, looks like that. Let's say x2 right, stays exactly the same direction but just gets longer. Okay, so we'll call this x prime 2. And then let's say with x3, that vector x3, I don't know, it rotates and maybe goes a bit longer as well. So now x3 goes like this. Okay, so essentially what's happening is that because x prime of 2 is just some scalar multiple of x2, right? Because after the transformation, the direction hasn't changed, it's just gotten longer, we would actually say that x2 was an eigenvector of the original matrix A. And that lambda, the scale factor after the transformation, is the corresponding eigenvalue. Okay, now, why is it that x1 can't be an eigenvector? Because x1 is essentially a line looking like that. So if I take this and have it like this, then clearly x1 has been deflected from that line. So it's not actually an eigenvector. It's not been multiplied by some scalar. Otherwise it would just still be on that pink line, but maybe a different direction. And then if I take x3, it should lie on this line. But clearly, if I take that over, then x3 is no longer on that orange line. It's now deflected over to here. So it can't be an eigenvector either. Whereas, if I've done this right, x2 must be an eigenvector, because if I take this green thing, oh, okay, so I've made a mistake maybe. Okay, so I've not done this properly. Stop it. This should be like that, maybe. Let's take this back. That should be there. Yeah, something like that. Because that x2 is still parallel, or it's supposed to be, ignore my bad drawing, then that is indeed an eigenvector. And it's really important, actually, to understand these intrinsic values of matrix transformations, because they tell us a lot about what's actually going on. If you're interested, then in quantum mechanics, we talk about things called eigenspinors. Looks like it should be pronounced eigenspinors, but it's S-P-I-N-O-R-S, eigenspinors, and essentially they are the intrinsic quantum state of a potential problem or an energy potential problem in quantum mechanics. And I don't know, maybe in a couple of months when we've done a bit more algebra and maybe we've done a bit more mechanics and we've looked at some second order partial differential equations, i.e. the Schrodinger equation, then maybe we can attempt that kind of stuff. But at the moment, let's crawl before we can run, before we can walk, run and jump. And let's get this idea of eigenvalues and eigenvectors down. So hopefully that's a motivation of why eigenvalues and eigenvectors are important, because we use them to answer more difficult problems. It's not just in quantum mechanics, it's in all kinds of engineering problems. I'm pretty sure you use them for stress and strain of building materials, that kind of things, pressure points, where particular things are going to break, building safe buildings, that kind of thing. They're just really important. For example, if you see this transformation as some twisted object, or rather some twisting, whether through pressure or through an earthquake or something, then essentially what's happening is the eigenvector is the part of that object that's not being affected by that strain, right? Because it's just twisting about that plane, and it may be elongated or whatever, but in actual fact it's not being bended or distorted, it's just kind of being stretched in that direction. It's really important. So let's stop clacking. Let's actually talk about how we find eigenvalues and eigenvectors then. So I'm going to need a couple of pages thinking about it. Okay, so how to find an eigenvalue and an eigenvector. And by the way, finding eigenvalues and eigenvectors, this stuff is in the further maths course, but only if you're doing FP2. But if you're doing a maths degree, for sure, just in the very basic first year linear algebra course, you know what, I would judge a university that would not be talking about diagonal matrices, eigenvectors, eigenvalues, all that good stuff, orthogonal stuff, if that wasn't done in either the first year, or it should be really the first term. It's just crucial. Same with linear ordinary differential equations. That should just be a thing. If you're doing any kind of maths and science degree, you should know how to deal with linear algebra, and you should be able to deal with ODEs, but never mind. So, I mean, you could do a further maths A level and never actually see eigenvalues and eigenvectors. If you're on the Edexcel spec, then it's in the FP2 module, so you'd have to be doing FP1 and FP2. This pretty much is beyond the course now. I can't remember if we've done anything beyond the course, but if you're interested in university mathematics, then let's get going. So, how do we find eigenvalues and eigenvectors? Well, what we do is we start with the definition, and that is if we have a square matrix A and we multiply it by a vector x, and that is equal some scalar multiple of that matrix x, scalar multiple of the column vector x, like that. Now, we want to solve for x, right? So what we're going to do, I want to solve for either x bar or lambda. I want to find one of those two things, right? So what we could do is we could minus them from one side. So a x bar minus lambda x bar equals to 0. Now, what can happen here? Well, it's very similar to what you'd expect. You'd expect that this to factorise to a minus lambda, and I'm leaving a gap there deliberately, times by x bar equals to 0. Now, there's a couple of things here. One, A is an n by n matrix, and lambda is a scalar. So it doesn't make sense to have something like this, say 1, 2, 3, 4, and then say minus 5. That's just not a thing we do. That just doesn't make sense. And we can't do it. So to get around that, what we do is we multiply lambda by the identity, the n by n identity. So now we've got two matrices that have similar or exactly the same dimensions, and now that subtraction actually makes sense. So everything's conserved. And by the way, this is still fine, because if I was to go back to here, lambda xn, for example, lambda x would still be the same as lambda times the identity times x. That would still be fine. I mean, it still works. Yeah, I mean, you can verify that for yourself if you want to, i.e. can you prove that lambda, x, y, z, and so on is the same as lambda, 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 and so on down the diagonals and 0 everywhere else equals then x, y, z, and so on as much as you like. You can start with the 2 by 2 case or the 3 by 3 case. You can verify this for yourself. If you're feeling really brave, you can do it proof by induction if you want to. And I kind of feel like I've given you the legs on that one to do it. Now, okay, so there's two solutions, right? You can either say, just like we've seen before, either x bar equals to 0, i.e. x, y, z, and so on for an n by n matrix is just 0, 0, 0, and so on. This is what's called a trivial solution, because if I multiply anything by the origin, 0, 0, 0, of course I'm going to get 0. It's essentially saying the vector that is the origin, i.e. go nowhere from the origin, doesn't change, because when I do some multiplicative transformation, I'm still at 0. So we're going to call that a trivial solution. We're not particularly interested in that. Of course, after some multiplicative transformation, the origin is not going to change. So we're not interested in that. What we are interested in is this over here. Okay, and the way we're going to deal with this is the following. We are going to solve for the determinant of a minus lambda in and set that equal to 0. Okay, now why would we do that? Well, because if we ignore the determinant and we set it equals to 0, then that's just not going to make sense particularly, because what would happen is we'd equate element with element and we'd find that a 0 doesn't equal 2 and so on and so on. What we want is we appreciate there is no solution to this. So by taking the determinant of this thing and setting it equal to 0, that's essentially saying they cannot be directly equated to each other. Therefore, let's find a particular value for which it does work. And now this becomes really easy to sort out. If I take an example of a 2 by 2 matrix, then let's say I want to find the eigenvalues of, let's say I've got 1, 2, 3, 4. Okay, and let's call this A. Then what I do is A minus lambda in, well that just means A minus lambda in will just translate to 1 minus lambda, 2, 3, 4 minus lambda. What happens is you just subtract lambda from this thing, which is called the leading diagonal. And now all we need to do is find the determinant of this thing, which is 1 minus lambda, 2, 3, 4 minus lambda. So this will become, and as you should know from 2 by 2 determinants, it's that times that, which is 1 minus lambda times by 4 minus lambda, and then subtract this product, 2 times 3, which is 6. And now I need to set this equal to 0 and solve for lambda. This thing here, right, very important, is called the characteristic equation of the matrix A. And now if I expand this, I will get, well, what happens if I expand this? I've got minus lambda times minus lambda, so I'll have a lambda squared. I'll have 4 times minus lambda, so it's minus 4 lambda. Minus lambda times 1, that's another minus lambda, so that's minus 5 lambda. I'll have 4 times 1, which is 4, but then I'll have a minus 6, that becomes minus 2. So now I have lambda squared minus 5 lambda minus 2 equals to 0. Okay, and now we just solve for lambda. Maybe there's solutions, maybe there's not. I just made this up on the spot, so who knows? So I'm probably going to complete the square on this. So lambda minus 5 over 2 all squared minus 25 over 4 minus 2, which is minus 8 over 4 equals to 0. So lambda minus 5 over 2 squared equals 25 plus 8, I believe, is 33 over 4. Square root both sides, lambda equals 5 over 2 plus or minus root 33 over 2. Okay, and now what we've actually got is two lambda values. We've got lambda equals 5 plus root 33 over 2, and we've got lambda equals 5 minus root 33 over 2. So as you'd expect, from a 2 by 2 matrix, we're going to have two eigenvalues. They may be the same, they may not be, they might not even exist. It depends on the characteristic equation of A. Okay, If it was a 3 by 3 matrix, you will have 3 eigenvalues to find. They might all be the same. There might be a pair of repeated ones. They might be distinct, but you're always going to have at least one, because that's generally how cubics work. For the purpose of assessments, you're only ever going to see 2 by 2 and 3 by 3 matrices to deal with. The idea is that for matrices of higher order, like 4 by 4s, 5 by 5s, and so on, you generally get computers to work with them. And as long as you understand the basics of what's going on, it's just computation. Okay. Now, for the purpose of this, I don't like the fact that 5 plus root 33 over 2 and 5 minus root 33 over 2, they're just not particularly nice numbers. So what I'm actually going to do is I'm going to repeat this example. So we've found the eigenvalues. Now let's suppose in a different example, and I'm going to pick the numbers deliberately easier this time. Let's say I've got 0, 1, 1, 0. I want to find not only the eigenvalues, but the corresponding eigenvectors. Okay, so hopefully this works out a bit easier. So let's call this matrix A. So let's suppose my job is I want to find the eigenvalues and their corresponding eigenvectors. So let's repeat what we've just done. I want to find the determinant of subtract lambda from the diagonals. And I want to set this equal to 0, and I want to find the determinant of that new matrix when it's equal to 0. So this will be quite easy. This is lambda squared plus 1, isn't it? Ooh, I don't want that, do I? No, it's not, silly boy. It's minus, isn't it? It's that minus this, that's minus 1. Okay, cool. So now this is pretty obvious, actually. I knew I picked this for the right reason. So this just means lambda is going to be plus or minus 1. So that's really easy. So either lambda equals 1 or lambda equals negative 1. So there's multiple ways you can do this. To find the eigenvectors, you can either use a times x equals lambda times x, right, and solve for x, or you could do a minus lambda in times the x and set it equal to 0. And all we're doing is going back to this definition up here in orange, of what an eigenvector and eigenvalues are found as. You know what? I'll do one of each way. So let's suppose for lambda equals 1, then I've got the matrix A, which is 0, 1, 1, 0, times by some column vector x. Let's be anything. Let's say x and y. And this equals lambda, which is 1, times by that same column vector x, y. Well, when we do the expansion, first row, first column, is just going to give 0 times x plus 1 times y, which is y, and this equals 1 times x, which is x. This just gives y equals x. By the second row, you can probably see that 1 times x plus 0 times y equals 1 times y. And now you're thinking, okay, y equals x, x equals to y. What does that mean? Well, remember, you're finding vectors that don't change direction, only get scaled up after this transformation. So that means they're not unique. For example, I could have had x2 being only that long, or I could have an x2 being that long, and so on. Or I could have had x2 in the opposite direction, but still parallel. The point is, I can have any scalar multiple. It's only the direction, orientation of that vector that really matters. So what this is actually saying is that as long as x equals to y and y equals to x, it doesn't matter what the vector is. So I'm just going to pick a really easy one, 1, 1. X is 1, y is 1, y equals x. So for when lambda equals 1, a corresponding eigenvector, let's call it v, well actually I've called it x, so I'll stick with x, is just going to be 1, 1. Easy peasy. Lemon squeezy. Okay, let's try another one. Well, let's try for the other one. When lambda equals -1, well, I'm going to have this vector, or this matrix of A minus lambda. Now, if lambda is already -1, then that means I've got 1, 1, 1, 1, if you think about it, because minus minus 1, remember, we've got negatives in the top left and bottom right, so just to make that clear, I've got minus minus 1 and minus minus 1, which is the same as 1, 1, 1, 1. Then I've got 1, 1, 1, 1, x, y, equals 0. Okay, so let's do that row by row. So multiply these vectors out and have this times this. So I've got 1x plus 1y equals to 0. And then from the other combination, then 1 that times that. I'm clearly just going to have the same thing, x plus y equals to 0. So as long as I have a vector that satisfies this, i.e. if I add x and y together, they're going to equal to 0, that's totally fine. So for lambda equals -1, an eigenvector, for example 1 minus 1, would be fine. Because if I add x is 1 and y is -1 together, I do get 0. So in actual fact, this is the eigenvalue of -1, and x is 1 minus 1, and they are corresponding, and these two eigenvalue and eigenvector corresponding pairs are done as well. So I have found both eigenvalues and their corresponding eigenvectors for this fairly simple 2x2 matrix. You can expand this to 3x3s by finding determinants and all that stuff. It's absolutely fine. Okay. Finding eigenvalues and eigenvectors for 2x2s and 3x3s should be fine now. We're now going to play around with this a little bit. We haven't quite finished. So, let's suppose I've got a matrix. So, suppose I've got a matrix looking like this. I've got loads of different numbers going down the leading diagonal, but zeros everywhere else. Okay, when a matrix is like this, it's called a diagonal matrix. Okay, it's called a diagonal matrix. So an example of a 2x2 well, this is an example of a 4x4 diagonal matrix. A 2x2 diagonal matrix could be something like 10, 20, 0, 0. That would be a 2x2 example, and so on and so on. You get it. The whole point is, along this diagonal, there's numbers. They don't have to be positive or negative. For example, this could be a -3, and that could be a 1,000, and this could be 2/3. It doesn't matter as long as they're numbers, real numbers. Could be imaginary in all fairness. As long as they have some value, they're non-zero. That's the main thing. Well, to be fair, they don't even necessarily have to be. These ideally have to be non-zero. But the point is, everything else must be 0. Okay, 100%. Everything that's not in the diagonal must be 0 for this to be a diagonal matrix. Now, this is hopefully going to blow your mind. I'm going to claim to you the following. That D, which is a diagonal matrix of ordered eigenvalues, is going to equal P inverse times by A, P, and it's going to be ordered eigenvalues of the matrix A. P is going to be a n by n matrix. By the way, these are all square matrices. These are all n by n matrices. It's going to be an n by n matrix with columns of eigenvectors ordered, that's important, of A. Now this is a really key result. This essentially is the way we diagonalize a matrix. Now why is that really important? Because essentially that turns any matrix into just an enlargement matrix within each individual coordinate systems. So it turns a matrix from what should be horrible, like 2, 3, 5, 2, and then we do stuff to it either side, and then it will spit out something nice like 1, 3, and 0, 0, where the x coordinate gets multiplied by 1 and all the y coordinates get multiplied by 3, and so on. Really cool. You might be thinking, oh God, well, what's the point of that? Later on, when we do a little bit of physics, being able to diagonalize matrices is so important because well, as I said before, you want to know eigenvalues, you want to know scale factors of which directional components of vectors remain unchanged, or rather their orientation doesn't change, they're just being enlarged by a scale factor. And essentially being able to have mastery over this just puts you in good stead for other things as well. So if I use this other example back up here, let's convince ourselves. Let's have an example of how this would work. So remember, from the previous example, remember that what did A equal? It equaled 0, 1, 1, 0. And that when lambda equals 1, then my eigenvector was 1, 1. And that when lambda equals to 2, not 2, lol, the second one. So we'll call this eigenvalue 1, eigenvector 1. Let's call this eigenvalue 2, which is minus 1. So the corresponding eigenvector x2 was 1 minus 1. Then I'm claiming, apparently, that if I order, then the claim is that if I have a diagonal matrix of the eigenvalues, so let's put 1 there for the first eigenvalue and 1 there for the other eigenvalue and put the rest in 0, this is going to be square matrix, square matrix, square matrix. The middle one is A, so this is D, this is the inverse of P and this is P. The matrix A, remember, was 0, 1, 1, 0. P is where I take the corresponding eigenvalues. So because the 1 went first, I need to put that one first. So that's 1, 1. And then because the minus 1 went second in the second column, I need to put the corresponding eigenvector in the second column, like so. Now, if you want to, you know how to find the inverse functions of 2 by 2 matrices. It's very easy. It's 1 over the determinant of that matrix, P. And then remember, we swap top left and bottom right, these two. So that'll become a minus 1 there and a 1 there. And then we change the sign of the opposite two. So these both become minus 1s. Now the determinant of the original thing is 1 times minus 1, which is 1, minus the other one product, so 1 times 1 is 1, so minus 1 times minus 1 is clearly minus 2. So it's going to be 1 over minus 2 times by this thing, so I times everything in there by minus 1 over 2, so that'll become positive a half, positive a half, positive a half, minus 1 half. So I'm claiming if I do this matrix multiplication, I'm claiming if I multiply these three matrices on the right hand side, that apparently it will equal the diagonalized form of 1, 0, 0, minus 1. Okay, I'll tell you what, let's just do that step by step. Let's multiply these two matrices together. Okay, this row, this column to get the first row, first column. So 1 half times 0 plus 1 half times 1 is 1 half. Easy enough. Next, because I want the first row, second column, 1 half times 1 plus 1 half times 0, that's just going to be a half again. Okay, now I want the second row, first column, so second row, first column. I'm clearly going to have a half times 0 plus minus a half times 1, so that's going to be minus a half. Okay, now I want the second row, second column, so second row, second column. I've got half times 1 minus half times 0, it's just going to be a half. Now to complete this, I've got to multiply this by 1, 1, 1 minus 1. So what will these two matrices get when you multiply them together? Well, they're going to create a 2 by 2 now. So first row, first column, first row, first column. I'll have half times 1 plus a half times 1, so that's a half plus a half, which is just a 1. Okay. First row, second column, first row, second column. I'm going to have a half times 1 plus a half times minus 1, so I've got a half minus a half. That is actually a 0. Okay. Now I want the second row, first column. So second row, first column, I'm going to have minus a half plus times 1, which is minus a half, plus a half times 1, which is plus a half, and that net result is going to be a 0. And then finally, on the second row, second column, so second row, second column, I'm going to have minus a half times 1, which is minus a half, plus a half times negative 1, which is another minus a half, and minus a half plus another minus a half is just going to be negative 1. And lo and behold, this is the same as what we were supposed to be getting up there. Okay, so that's how that's an example of how the diagonalization would work. Now, on your calculators, you have the matrix function built into the Casio CG50 and the Casio FX991EX. If you're unsure how to use it, unfortunately I can't get the calculator up on the screen to show you. It's unlikely I'll be able to figure out that software limitation, but yeah, you're just going to have to deal with it, learn yourself. There's so many tutorial videos online. I mean, that's essentially what I do. They're only 2 or 3 minutes long, so don't worry about it. I mean, I'll talk out loud what I'm doing. But yeah, there's only a couple things left, actually, I want to go through. Why are diagonal matrices so nice? So here's one property. So what's nice about a diagonal matrix is it has the following. Now, you know when you multiply two matrices, even if I have something simpler like 1, 2, 1, 2, if I was to square that matrix, that would not equal 1, 4, 1, 4, i.e. square the components. I mean, if we were to do that, 1, 2, 1, 2, so that does not equal that. Let's see what happens. So suppose we want to evaluate this. Well, what would happen here is 1, 2, 1, 2. I'd have 1, 2 times 1, 1. So it's going to be 1 times 1, 2 times 1, that's a 3. And then if I want that element, it's going to be first row, second column. So I believe that's a 6. And then if I want the second row, first column, second row, first column, it's 1 times 1 plus 2 times 1. So it's going to be 3 lots of 1s, that's another 3. And you can probably tell by symmetry, actually, it's going to be 3, 6. Clearly, these things don't equal to each other, so that's just dumb. What's nice about diagonal matrices is suppose this diagonal matrix is, say, A, B, C, and keep going, and the rest of these are zeros. And to denote their zeros, I'll just put big clouds of zeros like that. Okay, that just means there's 0 elsewhere. Then the great thing about this thing is if I raise D to the power n, then this matrix A, B, C, and so on with zeros everywhere to the power n, and this is actually just A to the n, B to the n, C to the n, and so on, and zeros everywhere else. If you'd like to verify this for yourself, go for it. But this is actually a really useful way of multiplying matrices really, really quickly if you're just interested in the transformations. i.e., if you want to keep transforming something again and again and again and again and again, instead of doing multiple transformations of this thing, you can just diagonalize it, raise that to a power, and then undiagonalize it if you'd like. Well, you don't necessarily have to, but the point is you can diagonalize and undiagonalize as much as you want. For example, it's pretty obvious if I've got this like that, then clearly if I apply the P matrix from both sides, and then or from the left hand side, and I apply the inverse from the right hand side, then clearly the matrix A is just P, D, P inverse, like so. And, you know, you can work backwards quite happily with that. It's just nice. Now, the final thing I wanted to mention, and it's called the Cayley-Hamilton Theorem. And this is actually really good, sometimes, of working out inverses of matrices that aren't particularly nice. And do you remember the characteristic equation? Okay, do you remember this thing when we did the determinant? Once we've subtracted lambda, which is the eigenvalue we're trying to find, and set it equal to 0 after taking the determinant, then this is actually a really cool little theorem. And the Cayley-Hamilton theorem states that for a square matrix, or an n by n matrix, then the matrix itself is a solution to its own characteristic equation. So do you remember in our previous example we had 0, 1, 1, 0, and that led to a characteristic equation of lambda squared minus 1 equals to 0. Well, that is the same as saying replace lambda with the matrix. So we've now got 0, 1, 1, 0 squared minus 1, which is technically the identity matrix if we were to make it in matrix form. And apparently that equaling to 0 is a thing. Now, let's check for ourselves what's going on here. Let's have 0, 1, 1, 0 times by 0, 1, 1, 0, which is the square matrix, or that matrix squared. Well, let's do this again. First row, first column. 0 times 0 plus 1 times 1 is a 1. And then first row, second column. 0 times 1 plus 1 times 0, that's a fat 0. And then second row, first column. 1 times 0 plus 0 times 1, that's a 0. And then finally, second row, second column. 1 times 1 plus 0 times 0 is a 1. So now, actually, we're going to have this thing squared becomes the identity matrix, so that when I subtract the identity matrix, 1 minus 1 is 0, the 0 minus 0 is that, 0 times 0, 0 minus 0 is 0, and the 1 minus this one is also a 0, and this is commonly referred to as the 0 n by n matrix. So the Cayley-Hamilton theorem states that the matrix itself, when you substitute it in for lambda, in the characteristic equation, is itself a solution to that equation. You just have to be careful when you've got constants. Remember that it's a constant times by the n by n identity matrix. So nota bene, you know, you still have to multiply by a matrix like that. Okay, I think that's pretty much a crash course in eigenvectors and eigenvalues. If you've been paying attention so far, fantastic. Now, I've put a few questions in there on the old spec, and they're to do with vectors, i.e. straight lines, planes, that kind of thing. So this will be a nice little recap of all the stuff we've been learning so far. So what I'm going to do is I'm going to show you the question. I'm going to pause the video, as well as you pause the video. I just need to pop to the lavatoire. Back in a mo. Okay, so let's crack on with this. So the matrix M is given by that. Show the determinant of M is the following. Okay, right. So, when doing determinants of 3 by 3 matrices, you ideally want to pick a row or column that has as many zeros as possible. Now, I'm going to pick, you could have done the top row in all fairness. There's nothing wrong with that. But personally, I'm going to use the middle row. The following. So, remember, when doing determinants, you've got this plus minus checkerboard thing going on. So you've actually got -1, lots of. Now if you're going from this 1, it's -1, you cross out that row and that column. So now you've got the -1 times 1, which is -1, minus the 1 times -2, which is a -2, plus 0, which you don't have to worry about because it's times by 0, and then a minus -1, so that becomes a +1. And now, if you ignore that row and that column, then I've got k times -2, which is -2k, minus a -1 times 3, which is a -3. Okay, well there's not a lot to do here except just expand them out. So -1 minus -2 becomes that +2. -1 plus 2 is just +1. -1 times 1 is -1. That term's gone. And then I'm going to have 1 lots of -2k minus -3, which is +3. Well, that's pretty easy to sort out because -1 plus 3 is 2. And then I've just got a -2k. So yes, the determinant is 2 minus 2k. Find the inverse of M in terms of k. Right. Okay, so there's lots of things to do here. Remember, you've got to do 1 over the determinant, which is 2 minus 2k. You've also got to find the matrix of minors, which is taking the determinant of each little thing. So really I should have done my workings for that. So I can fill out the middle row at least. So in here I had -1 plus 2, so that should have been a 1. For the 0, technically I'd have had k times 1, which is k, minus a 1 times 3, so that's a k minus 3. And then for the -1, I would have had 3 minus 2k. Okay. What else do I need to do? I need to, so for the matrix for this k thing up there, I need to find the matrix of k. It's a 0 times 1, that's nothing, minus 2 times -1, so that's a 2, so that would just be a -2 up there. And then -1, so I take the determinant at that point, so 1 times 1 is 1, minus 3 times -1 is -3, 1 minus -3 will give a 4. And then for this one, I've got a 1 times -2, which is -2, minus a 3 times 0, so that's a -2. Then for the 3, I'm going to have a -1 times -1, which is a 1, minus a 0, so that's a 1. And then I'm going to have, from that one, k times -1, which is a -k minus 1, so it's -k minus 1. And then from this one, I'm going to have k times 0 minus a -1, so that's a 1. And then remember, there's 4 things. I always get this wrong. There's 4 things when doing the inverse of a 3 by 3 matrix. One of them is 1 over the determinant. One of them is finding the matrix of minors, which I did. I believe we have to transpose it actually. Thinking about it, so I know I'm going to have the transpose in there. There's a fourth thing. I want to say I have to do the plus minus checkerboard. Yeah, so find the determinant, done that. Form the matrix of minors. From replace by minor, yeah, done that. Yeah, okay. I now have to do the plus minus checkerboard thing. Okay, so that will be plus minus plus, and then minus plus, and then minus, that becomes minus 3 plus 2k, and then plus minus, so that'll become a plus, and that'll become a plus down there. And now I just need to transpose it. Well, so this will become, so the inverse of m is going to be 1 over 2 minus 2k, and then the transpose means I keep the diagonals as they are, so minus 2k minus 3, 1, and then I flip across the diagonal, so the minus 4 will now go there, and that's minus 1. That'll be minus 2. Oh no, that minus 2 switches with the 1, so the 1 and minus 2 flips there. And then this will be k plus 1, and this will be minus 3 plus 2k. Okay, right, cool. Okay, right, the straight line L1 is mapped onto the straight line L2 by the transformation represented by the following. Okay. The equation of L2 is that R minus A cross product B equals to 0, where A is that and B is this. Find a vector equation of L1. Okay. So, what is this saying? This is saying if I've got a general point, the equation of L2 is a point. By the way, R could just be some point, let's call it A, B, C, and then it's plus some lambda of, what is it? I don't know, something else, D, E, F, and apparently when I subtract A from that, which is 4, 1, 7, because that's what 4i, j and 7 is, and if I cross that with 4, 1, 3, then I get nothing, I get a 0. Okay, so let's think very carefully what that means. So if I have A minus 4, B minus 1, C minus 7, plus lambda D, E, F, and I need to cross that with 4, 1, 3. Okay. Actually, hold on a minute. What is the cross product? What is the cross product again? The cross product is A cross B. It's A, the mod of A, mod of B, sine of the angle between them times by the unit normal vector n. So for the cross product equal to 0, the mod of A doesn't equal 0, the mod of B doesn't equal 0, otherwise this is just 0 times 0. The unit normal vector doesn't equal 0, so that means sine theta equals to 0. And for sine theta to equal to 0, theta equals 0 or 180 degrees or some multiple of 180, or pi radians if we're dealing with that. So that must mean these two vectors are parallel. So actually I don't think I need to do this complicated system of equations. I know that for my line L2, R is going to be something plus some multiple of this vector b, which is 4, 1, 3. Okay. So if I know that's the case, well, I know that R equaling to A would be a solution for this, because 0 cross B would also equal to 0. So I know that A must lie on this line as well. So that must be 4, 1, 7 lies on the line too. So actually, I can say with, accuracy that the line L2 has equation like that, if I was to write it in vector form. So if I was to write that, I'm going to need more space, aren't I? If I was to write that in terms of x, y, and z, then let's say x, y, z is the column vector, and this is for a general point in L2, then if I apply the inverse matrix of that transformation, and it was let's call this matrix A, then it will output L1 for the x's, y's, and z's. Okay, so what is the x coordinates and y coordinates for this line L2? Well, it's going to be 4 plus 4 lambda, 1 plus 1 lambda, and 7 plus 3 lambda. So if I can do the inverse of 4 plus 4 lambda, 1 plus lambda, and 7 plus 3 lambda, then this will give me the x1, y1, and z1 coordinates on the line L1. Fine. Well, how do I find the inverse of this thing? Well, if you look very carefully, it's just when k equals to 2. So if I use this inverse when k equals to 2, I'm going to have 1 over 2 times 2 minus 2 lots of 2s. 2 minus 4 is minus 2. And then I'm going to have, what is it, minus 2 minus 1, 1. And then minus 4, and then 2 minus 3 is minus 1. 2 plus 1 is 3. And then minus 2, minus 3 plus 2 lots of 2 is minus 3 plus 4, so that's a 1. And then this is a 1, and I need to multiply this by 4 plus 4 lambda, 1 plus lambda, and 7 plus 3 lambda. Okay, now what I'm going to do is, this is a 3 by 3 matrix, and it's being multiplied by a 3 by 1 matrix. These are the same, so it's going to output 3 by 1, which is just what I wanted. I am going to put the half on the outside, the minus half on the outside, because I'm just going to do the matrix multiplication first. And then what I'm going to do is, I'm actually going to do over this twice, but simplify as I go. So I'm going to do first row by first column, but I'm going to do the numbers first, and then I'm going to do the lambdas. So numbers first, I've got minus 2 times 4. So let's just calculate this. I've got minus 2 times 4, which is minus 8. And then I've got minus 1 times 1, which is minus 1. And then I've got 1 times 7, so plus 7. So minus 8 minus 1 plus 7 is actually minus 2. And then sweeping through that again, I've got minus 2 times 4 lambda, so I've got minus 8 lambda. I've got minus 1 times lambda, so that's minus 1 lambda. And I've got 1 times 3 lambda, so minus 8 minus 1 plus 3 will give minus 6 lambda. So that's that done. And now for the second row, first column. Let's do the numbers first. So I've got minus 4 times 4, which is minus 16. I've got minus 1 times 1, which is minus 1. And I've got 3 times 7, which is plus 21. So that's going to give a nice positive 4. And then for the lambdas, I've got minus 4 times 4, which is minus 16. I've got minus 1 times lambda, which is minus 1 lambda. And 3 times 3 lambda, which is plus 9 lambda. So that's going to give a minus 8 lambda, like so. And then for the final entry, Seems a bit tedious, but this is the way to go. I've got, for the constants, minus 2 times 4, which is minus 8. I've got 1 times 1, which is plus 1. And I've got 1 times the 7, so that's plus 7. So that's just going to be a big fat 0, so that's fine. And then for the lambdas, I'm going to have minus 2 times 4, which is minus 8. 1 times 1 lambda, which is plus 1 lambda. And 1 times 3, so another plus 3 lambda. So it's actually going to be negative 4 lambda. Now remember, for L1, there's a minus half out there. So if I distribute minus half into all this, minus half of minus 2 is 1. Minus half of minus 6 lambda is plus 3 lambda. 4 minus half becomes minus 2, and minus half of minus 8 becomes plus 4 lambda. Then minus half of minus 4 lambda is just positive 2 lambda. So in actual fact, the equation of the line L1 is just going to be 1 point, which I know is 1 minus 2, 0, plus lambda lots of, and then the coefficients of lambda is 3, 4, 2. If you want to write this as I, J and K, then it's completely up to you, but I'll leave it as that. So yeah, tricky question. Okay, another difficult question. Pause the video, give it a go yourself. Okay, the plane pi1 has vector equation r blah 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 blah, where s and t are real parameters. The plane pi1 is transformed to plane p2, where the transformation represented as the following. Find an equation of the new plane pi2 in the form of the point dotted with its normal equals to p. Okay, right, so there's nothing for it. We're just going to have to write r as a 3 by 1 vector of 1 plus s plus t, and then minus 1 plus s plus 2t, and 2 minus 2t. All I've done is I've just gone row, 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 and outputted them there into a 3 by 1 matrix. I'm now going to multiply this 3 by 1 matrix, the 3 by 3 matrix, by the 3 by 1 matrix to apply the transform to it. And same as before, I'm just going to do, this is going to output a 3 by 1 matrix, and I'm just going to do row by column, but I'm going to do the numbers first, and then the s's, and then the t's. So first row, first column. And by the way, this is all a 3 by 1, so technically I'm doing the whole thing here. So 2 times 1 is 2, plus 0 times blah, plus 3 times 2 is plus 6. So the first term is going to be 8. And then with the s's, I've got 2 s's plus nothing else, that's plus 2 s's. And then I've got 2 times t, plus 3 times minus 2 is minus 6, so I've actually got minus 4t there. Okay, second row, first column. So numbers-wise, we've got 0 times 1, 2 times minus 1, which is minus 2, and minus 1 times 2 is another minus 2, so that's actually minus 4. Then the s's, I've got no s's, plus 2 times s, minus nothing, so I've actually got a 2s there. And then the t's, I've got 0t, plus 2 times 2t, which is 4t, plus minus 1 times minus 2t, which is another 2t, so I believe that's a 6t there. And then finally, last row, first column. So numbers-wise, 0 times 1, 1 times minus 1 is minus 1, and 2 times 2 is 4, so that's going to give a net result of 3. S-wise, there's no s's. Oh, don't be silly. 0 times s, 1 times s is a single s, and 2 times nothing. That's just going to be a single s. And then for the t's, I've got no t plus a 2t minus a 4t, so it's actually going to be a minus 2t. Is that right? Yes. Okay. So find an equation of the plane in terms of r dot n of that thing. Okay, so if I write this out properly, r in terms of pi 2 is going to be the number terms, which is 8 minus 4, 3, plus how many s's? Well, the coefficient of s's is going to be 2, 2, 1, plus the amount of t's, which is minus 4, 6, minus 2. Okay, so to find the normal, that's going to be pretty easy. All we need to do is the determinant of the Ijk matrix with 1 matrix 2, 2, 1 as one row and minus 4, 6, minus 2 as another. So this is going to be I lots of, take that out. 2 times minus 2 is minus 4. Minus a 6 times 1 is minus 6, so that result is a minus 10. And then minus j lots of, and then cross out the j row and j column. I've got 2 times minus 2, which is minus 4, minus a 4 times minus 1, which is a plus 4, so I believe that's a big fat 0. And then for the k one, so remember the checkerboard, it's plus k now, so that becomes 2 times 6, which is 12, minus 4 times 2 is minus 8, so 12 minus 8 becomes a 20. Okay, so we've got a perpendicular vector to the plane of minus 10, 0, 20, but I could equally valid to have, say, minus 1, 0, 2. I can just scale it down. So if I take a point on the plane, which I know to be 8, minus 4, 3, because that's a point R, and I dot it with the normal vector, which I'll take it as minus 1, 2, 0, then this will equal 8 times minus 1 is minus 8, that times that is 0, 3 times 2 is 6, so that becomes minus 2. Arbitrarily, I could have made this a positive 1 and that a negative 2 to make that positive 8 and negative 6 to make that a positive 2. The reason why I do that is because now I can do R dot my n, which is now 1, 0, minus 2, and I can set that equal to 2, a positive constant. So in actual fact, my plane pi 2 has equation R dotted with 1, 0, minus 2 just equals 2. So my P equals 2 and my n value is 1, 0, minus 2 as a vector. Yeah, so when you can solve these questions fairly easily, I know we haven't looked at eigenvalues and eigenvectors yet, but this is, just recap of stuff we've done. Okay, here we're going to be looking at the Cayley-Hamilton. So yeah, pause the video, give it a go yourself. We're definitely using the Cayley-Hamilton theorem. Okay, so given that A equals that, find the characteristic equation of it. So the characteristic equation is if I write out the matrix and then I subtract lambda from the diagonal, so it looks like this, and then I take the determinant of this and I set it equal to 0. So if I take along the top maybe, just because there's ones there, I'll have minus 1 minus lambda, lots of, this times this, and minus lambda times that, if I tidy up as I go along, is actually lambda lots of lambda minus 3, because I just times by minus 1, and then minus 4 times minus lambda, that becomes plus 4. Okay. Now remember the checkerboard, I now have minus 1 lots of, and now if I go along there and there, then I've got minus 2 lots of 3 minus lambda, which is 2 lots of lambda minus 3. If I distribute that minus out, minus the 4 times 4, the other product going that way, so that's going to be minus 16. And remember the checkerboard for the final one. I've got in that one, so I've got plus 1 lots of, and then minus 2 times minus 1 is positive 2, minus 4 times minus lambda, well that's minus 4 lambda, so 2 minus minus 4 lambda is just 2 plus 4 lambda. And apparently this all equals to 0. So the characteristic equation is 0 equals. Now if I take a minus out, this becomes lambda plus 1. If I tidy all this up, I've got a lambda times lambda, which is a lambda squared. I've got a lambda times minus 3, which is minus 3 lambda, and that's plus a 4. And I've got minus, and then I've got 2 times lambda, which is 2 lambda, and then 2 times minus 3 is minus 6, and don't forget I've got minus 16, so that becomes a minus 22. And then plus, and then I've got the 2 plus 4 lambda here. Okay, Let's tidy up. I've got minus lots of. Now I'm going to have a lambda cubed popping out from lambda times lambda squared. In terms of lambda squared, I'm going to have 1 lambda squared there, but minus 3 lambda squared there. So it's a net result of minus 2 lambda squared. Now in terms of lambda, I'm going to have 4 lambda there and a minus 3 lambda there. So it's going to contribute to a positive 1 lambda. And then finally, in terms of the numbers, constant terms, I'm just going to have 1 times 4, so that's a plus 4. If I distribute the rest out, I'm going to have minus 2 lambda minus 22 is plus 22, and then plus 2 plus 4 lambda. If I tidy all this up, I'm going to have minus lambda cubed minus 2 lambda squared is plus 2 lambda squared. But then minus a lambda there is minus 1. So I've got a minus 1 lambda. I'm going to have a minus 2 lambda from here, so it's minus 2. And then I'll have a plus 4 lambda from the end one. So that's going to result in a positive plus lambda. So that's gone, that's gone, that's gone, that's gone, and that's gone. In terms of the numbers, I've got minus times positive 4, which is minus 4. And then I've got a plus 22, and then I've got a plus 2. So that's going to result in a positive 20. To tidy all this up, I'll times everything by negative 1 to get lambda cubed minus 2 lambda squared minus lambda minus 20 equals to 0. And I'm quite happy with that being my characteristic equation. Next, part B, show that that identity is the case. Well, by the Cayley-Hamilton Theorem, then the matrix A is a solution to this, i.e. 0 equals A cubed minus 2A squared minus A minus 20 lots of the identity matrix. Now, if I times everything by the inverse of A, then I'll have A squared minus 2A minus the identity matrix minus 20 lots of the inverse of A equals to 0. If I add that inverse to the other side, I'll get 20 lots of the inverse equals A squared minus 2A minus the identity matrix. And I believe that's what they wanted. A squared minus 2A minus the identity equals 20 lots of A to the 20 lots of the inverse of A. Part C, hence find A inverse. Okay, not particularly difficult. I'm going to use my calculator function. So what I'm going to do is math vector, go to my 3x3, and I'm going to type in, because they're all numbers, I'm going to minus 1 in the top, then 1, 1, minus 2, 0, 4, then 4, minus 1, 3. Okay, so that's saved as matrix A. So if I go option, matrix A, matrix alpha A, and I times that by matrix alpha A. Right, okay, so I get A squared is actually the 3x3 matrix of 3 minus 2, 6, 18, minus 6, 10, 10, 1, 9. Okay, let me just double check I've got that right, because I did have some other matrices saved in here. Minus 1, 1, 1, 2, 4. Yep, okay. And then I'll minus 2 lots of A. So what is 2 lots of A? Well, it's 2 lots of the matrix. So instead of minus 1, 1, it's minus 2, 2, 2. And then minus 4, 0, 8. And then 4, minus 1, 3. Oh, I've got to double it, you silly boy. 4 doubled is 8, minus 1 doubled is minus 2, and 3 doubled is 6. And then I have to minus the identity matrix, which is 1, 1, 1, zeros everywhere else. And then if we look at what that is, what's going to happen? I just do it term by term. 3 minus minus 2 is 5, minus 1 is 4. Minus 2, you know, I just do it. In actual fact, let's just do this. Exit. Let's in matrix B now. put them in as 3, minus 2, 6, 18, minus 6, 10, 10, 1, 9. Okay, so that's matrix B. So what I'm going to do is I'm going to do matrix, no, option, matrix B minus 2 lots of matrix alpha A. We'll give that, and then I minus 1 from the diagonal. So instead of 5 minus, so that's 4 minus, oops, that's minus 4, 4. Then I'll have 22, minus 6 minus another 1 is minus 7. And then that's a 2, and then 2, 3, and then 3 minus 1 is 2. And then don't forget, the inverse is when you divide all of that by 20. Yeah, because remember that 20 lots of the inverse is when I do all that stuff. So if I divide everything by 20, then I'm going to have 4 over 20 is a fifth, and then this is minus a fifth, and then 22 over 20 is 11 tenths, and then this is minus 7 over 20, 2 over 20 is 1 tenth, 2 over 20 is 1 tenth, that's 3 twentieths, and the last one is 1 tenth as well. So the inverse of the matrix is that. So actually that was quite nice, because we didn't actually, even if we forgot how to do the matrix of minors there, or any of that four-stepness, we actually found the inverse quite nicely. Okay. Right, how many more have we got? Oh, just 2. Okay. So pause the video, try and give this one a go yourself. Definitely got eigenvectors here this time. So the matrix M is given by that. Given that j plus k and I minus k are 2 eigenvectors, so j plus k means we've got 0, 1, 1 as an eigenvector. Let's call this x1. And another eigenvector, x2, is I minus k, which is 1, 0, minus 1. Find the values of a, b, and c. Okay, so what have we got here? We've got that, remember, if we have the matrix times x1, that is the same as the scalar times x1, or we could do a minus lambda in x1 equals to 0. And I think we're probably going to do that here. So I might use this one for no reason. So let's say I've got 1 minus lambda, 1a, and then 2b minus lambda, c, and then minus 1, 0, 1 minus lambda. This is times by 0, 1, 1. And this is going to equal 0. Well, it's technically the 0, 0, 0 matrix. Remember, the dimensions have to count. Now, if I take the bottom row that doesn't have a, b, and c in it, I can now work out what lambda is. So minus 1 times 0 is nothing. 0 times 1 is nothing. 1 minus lambda times 1 is 1 minus lambda. And that has to equal the bottom element there, which is 0. So immediately we can work out that lambda is 1. For this one anyway. So for this eigenvector, 0, 1, 1, the eigenvalue is lambda, is 1. So that's nice, because then now I can get rid of stuff. So 1 minus lambda, that becomes a 0. And then b minus lambda, that becomes a 1. Okay, so now I can proceed to go about and work things out, right? Because now if I do the first row, first column, that will be the top element, and I can now work out what a is. So I've got 0 times 0 plus 1 times 1, which is 1, plus a times 1, and that will equal to 0. So clearly a equals to negative 1. Okay, now we're just going to have to do simultaneous equations, because now if I take the second row, multiply it by the only column, I'm now going to, oops, not that, I'm going to get the middle one, like so. And then now all I need to do is just find the other one and we're away. So, okay, so we've got 2 times 0, which is nothing, b times minus 1, which is b minus 1, plus c times 1 equals 0. So if I add 1 to both sides, I get b plus c equals to 1. And now we can use the fact we've got another eigenvector and we can work out its corresponding eigenvalue to deduce other things. So let's do that maybe. I'm definitely going to be needing more space. So if I do my 1 minus lambda 1a, which I now know is minus 1, and then 2 b minus lambda c minus 1, 0, 1, and then times by that new eigenvector, which is 1, 0, minus 1, that must also equal 0, 0, 0. So now I can do top row, top column to get the first item to work out what the lambda is. So 1 times 1 minus lambda is 1 minus lambda. 1 times 0 is nothing. Minus 1 times minus 1 is plus 1. That equals to 0. So it looks like here lambda actually equals to 2. So now if I do the middle, so that corresponds to the middle element here, then I've got 2 times 1, which is 2. b minus lambda times nothing is nothing, and then c times minus 1 is minus c, and this equals to 0. Oh, I didn't even need to find out what lambda was. I don't know, maybe it's going to be useful in the next question. I don't know. In the next part of the question. Who knows? So if 2 minus c is 0, then c equals to 2, and if b plus c equals to 1, then b clearly equals to minus 1. So the solutions are a is minus 1, c is 2, and b is minus 1. Find the eigenvalues which correspond to the two given eigenvectors. Well, I've done that already as part of the question. Lambda 1 is 1, and lambda 2 is 2. Okay, the matrix P is given by the following, where D is a constant and D does not equal to minus 1. Find the determinant of P in terms of D and the inverse of P in terms of D as well. Okay, so can I minimize this stuff and save some space? So I can go up there. This stuff can be minimized and go here. This stuff can go there. Right, so from this point onwards, mate, this is BI. Okay, so I've got 1, 1, 0, 2, 1D, minus 1, 0, 1. Okay, what is the determinant of D? Well, I'm going to look for rows and columns that have zeros in them. So I'm probably going to go for that row just because. Remember, I've got the plus, minus, plus checkerboard. So this is going to be 1, lots of, and then it's going to be 1 times 1 minus 0 times D, so that's going to be a 1, minus 1, lots of, and then it's going to be 2 times 1, which is 2, minus a minus 1 times D, which is minus D, so that's a plus D, and then plus a 0 times by, and I'm just going to do it because I know it's going to be needed for the matrix of minors later, 2 times 0, which is nothing, minus a minus 1 times 1, which is a positive 1. So the determinant of this thing, so the determinant of P is just going to be 1 times 1, which is 1, minus 1 times 2, which is 2, minus D. So it looks like it's just going to be minus 1 minus D. Is that right? Yep, seems legit. And then part II, find that matrix inverted. So I'm going to need to do 1 over the determinant, which is minus 1 minus D. Then I need to find the matrix of minors. So because I went across the top, I can just fill these things in. So that's saving a bit of time. So 1, 2 plus D, 1. Then I need to find the determinant of the other thing. So from 2's perspective, I'm going to have 1 times 1 minus 0 times 0, so that's a 1. From the middle's perspective, I'm going to have 1 times 1 minus a 0 times minus 1, so that's also a 1. From the D's perspective, I'm going to have 1 times 0, which is nothing, minus a minus 1 times 1, which is a minus 1, so that's going to be a 1 as well. From the bottom left-hand perspective, I'm going to have 1 times D minus 1 times 0, so that's a D. From the zero's perspective, I have 1 times D minus a 2 times 0, so that's a D. And then from the bottom right, I'm going to have 1 times 1, which is a 1, minus 2 times 1, which is minus 2, so 1 minus 2 is a minus 1. And now I'm going to apply the checkerboard to this, so I've got a plus, this is a minus, that's a plus, that's a minus, that's a plus, that's a minus, that's a plus, that's a minus, and plus that. And then remember, I need to transpose all of this stuff. Right, so this is going to be 1 over 1 minus 1 minus D, and then the diagonals stay the same, so 1, 1, minus 1. This becomes minus 2 minus D down there, and that becomes a minus 1. The D pops up to there, and that's a 1 down there, and then I've got a minus D minus 1 here. And just for giggles, if I take a factor of minus 1 out the front, I'm going to have 1 over 1 plus D. And then if I put the minus 1 inside, I'm going to have minus 1, 1 minus D, 2 plus D, minus 1 positive D, minus 1, 1, 1. And that is my inverse of P. Coolsies. And that is the inverse in terms of D. Yeah. Okay. Last one, super promise. Just adding a page. Put it next. Hold on, let's take this. Move it there. What? Where'd it go? Oh dear, I added an extra page. I don't know where it's gone. Okay. Right, so pause the video, give it a go yourself. Okay, the matrix A is given by that. Show that 2 is a repeated eigenvalue of A and find the other eigenvalue. Okay, so let's find the eigenvalues. Remember, I need to take lambda away from the diagonal. So 3 minus lambda, 3 minus lambda, and then this is a minus 2, 2, minus 1, 2, minus 2. I'm going to take the determinant of this and set it equal to 0 to find the characteristic equation. So this is going to be 6 minus lambda, lots of, 3 minus lambda all squared, minus 1 times minus 1, which is a 1. Cool. And then I'm going to have a minus 2 if I'm going across the top. So it's going to be plus 2, lots of. And then it's going to be minus 2 times that, so it's going to be 2 lots of the other way around, minus lambda minus 3. Minus 2 times minus 1, so actually that's going to be plus 2. And then I've got a plus 2 for the last element, and I've got minus 2 times minus 1, which is 2, minus 2 times 3 minus lambda. Okay, let's pack things up. So 0 equals, and this is 6 minus lambda, lots of, 3 minus lambda squared. So that's going to be 9 minus 6 lambda plus lambda squared. And then I'm minusing 1, so actually that 9 is going to drop down to an 8. I believe. Yep. And then plus 2 lots of, well, 2 times lambda in the brackets, so it's going to be a 4 lambda when times by 2. And then 2 lots of minus 3 is minus 6. Minus 6 plus 2 is minus 4. Times by that is going to give minus 8. And then plus, and I've got minus 2 times minus lambda, so that's 2 lambda, times by 2 is 4 lambda. And I have minus 2 times 3 is minus 6, add the 2 is minus 4, times by 2, it's going to be another minus 8, isn't it? Okay. Lol, it's exactly the same. I don't know why I didn't see that. Yeah, lol. That's lol. Okay, fine. Well, let's have a look. So when I expand this stuff, I'm going to get a negative lambda cubed. How many lambda squareds am I going to get? Well, I'm going to have a lambda squared times 6, that's 6. and I have a minus 6, so it's going to be a plus a 12 lambda. In terms of lambdas, I'm going to have minus 36 from the minus 6 times that, and I'll have a minus 8. So am I going to have minus 44 lambda? Is that true? Yeah, and then I have plus 8 times 6, which is 48. And then for the other thing, I'm just going to have 8 lambda minus 16. So I'm going to have minus lambda cubed, no other lambda squareds to speak of. Is that true? Yeah, so that's plus 12 lambda squared. I've got minus 44 lambda, but then I'm adding 8 lambda, so that's going to give minus 36 lambda. And then I've got 48 minus 16, which I believe is 32. And if I times everything by minus 1, I get 0 equals lambda cubed minus 12 lambda squared plus 36 lambda minus 32. And now I just want to prove that 2 is a repeated eigenvalue. So for 2 to be a repeated eigenvalue, I need lambda 2 in there, or lambda minus 2 to be a factor. Well, is it? I can do algebraic long division on this, which will help. So I have lambda cubed minus 12 lambda squared plus 36 lambda minus 32. Lambda into lambda cubed is lambda squared. Lambda squared times these two is lambda cubed minus 2 lambda squared. Minus that over is minus 10 lambda squared. Bring the 36 lambda down. How many lambdas into the minus 10 lambda squared? That's minus 10 lambda. Times that in is minus 10 lambda squared plus 20 lambda. Minus that, they cancel. You're going to be left with 16 lambda minus 32. Bring this down. And then how many lambdas is 16 lambda? That's plus 16. And then 16 lambda, 16 times minus 2 is minus 32. The remainder is 0, is indeed a factor. So actually this thing can be written as lambda minus 2 times by lambda squared minus 10 lambda plus 16. And then this quadratic is quite easy to sort out because it is actually lambda minus 2 times by lambda minus 8. What two numbers add to minus 10 and multiply to positive 16? That's clearly minus 2 and minus 8. So we actually have lambda equals 2 as an eigenvalue, repeated, and we have lambda equals 8 is an eigenvalue. What did the question want? Show that 2 is a repeated eigenvalue and find the other one. Tick, boom, lambda is 2, lambda is 8, that's done. Hence find 3 non-parallel eigenvectors of A. Right, so let's just plug in. Well, because lambda 2 is repeated, I'll get to it in a second. Let's do the lambda equals 8 business. So same deal. If I subtract 8 from the diagonal, the matrix I'm going to get is 6 minus 8, which is minus 2, minus 2, 2. And then minus 2, and then 3 minus 8 is minus 5. And this is minus 1. And then 2 minus 1, and then the 3 minus 8 is another minus 5. And then that times by the vector x, y, z must equal to 0. Remember, we're doing A minus lambda, lots of the identity matrix, times by x equals to 0, because that's just how it rolls. Okay, so from the top row, we're going to have minus 2x minus 2y plus 2z, expanding this out, equals to 0. And by the way, this is the 0 matrix, like that. Okay, if I add x and y to both sides, hopefully you can see that x plus y equals to z. Okay, and then if I look at the next line, I've got minus 2x minus 5y minus z equals to 0. So if I add z to both sides, I get z there, and minus 2x minus 5y. And then I remember that z is x plus y, so if I have x plus y equals minus 2x minus 5y, then if I add 2x to both sides, that's 3x. If I minus y to both sides, it's minus 6y. Divide by 3, x equals minus 2y. That's nice. And now if I look at the bottom row, I'm going to have 2x, multiplying this out, minus y minus 5z equals to 0. I know what 2x is. That's minus 2y. So 2x is going to be minus 4y. This is minus a y. and then minus 5 lots of z, which is x, which is another minus 2y, plus a y, and this equals to 0. Well, this should all work out for this to be consistent. So minus 4y minus a y is minus 5y. Minus 2y plus a y is minus a y again. And clearly minus 5 times minus y is plus 5y, and minus 5y plus 5y cancel out. So it doesn't tell us anything particularly new. So now all I have to do is pick a vector that satisfies these two things. The third row satisfies and agrees with the other two, so that's fine, it's consistent. So all I have to do is pick a value of x or y and fudge it in for z. So because this x is a function of y, I'm going to let y be 1, and I know x is minus 2 lots of that 1, so that's minus 2, and z is what happens when I add those two together, so minus 2 add 1 is going to be negative 1. So this is one example of an eigenvector that works, and this is for lambda equals to 8. So that is a multiple of an eigenvector for lambda being 8. Now let's look at the repeated one, and lambda is 2 in this case. So 6 minus 2 is 4, then that's minus 2, 2, then minus 2, 3 minus 2 is 1, minus 1, 2 minus 1, 3 minus 2 is a 1. So if I copy this, bring it down south, and I'll do the exact same thing, and that is this thing times by x, y, z should equal the 0 vector. Okay, multiplying across the top, I've got 4x minus 2y plus 2z equals to 0. So that means y equals 2x plus z if I add 2y to both sides and divide by 2. So that's fine. Next up, I'm going to have minus 2x plus y minus z equals to 0. And if you look at that, that's y equals 2x plus z again. So that doesn't actually tell us anything new. And then for the bottom row, I'm going to have 2x minus y plus z equals to 0. So if I add y to both sides, again, I get 2x plus z equals to y. Whoop-de-doo. So as long as I pick a vector that satisfies that, I'm away. So for no particularly apparent reason, let's pick x equals to 0 to make our lives a bit easier. Well, if x equals to 0, look what happens. I've got 0 plus z equals to y, so z equals to y. That just means when x is 0, I could just have 1, 1, and then that's perfectly fine. So that's one possible solution. Now, because it's repeated, so we'll call this x2, because this is repeated, I'm going to need another eigenvector from this. So let's now pick y equals to 0 and see what happens. Well, if y equals to 0, what does happen? Then actually 2x equals minus z, or rather z equals minus 2x. So as long as if I multiply x by minus 2 I get z, this will also be a valid eigenvector. So if I pick, say, x is 1, then z would have to be minus 2. And now, clearly, they are parallel. Sorry, they are not parallel, lol, because they're not multiples of each other. There's no way I can multiply this column vector by a scalar, by a number like 2, 3, 5, and it would produce this over here. So in actual fact, I now have produced 2 eigenvectors for that repeated one over there, and 1 eigenvector for this one over here. They're not unique, by the way, so don't beat yourself up if your eigenvectors aren't similar to mine. So that's done. Find a matrix P such that P inverse AP is a diagonal matrix. Well, lol, if you'd been listening, P is just a matrix where the eigenvectors are just columns. So if you wanted the diagonal matrix to go 2, 2, 8, like that, then in the first two columns I'd have to have the two eigenvectors to deal with lambda equals 2 first. So in any order, because they're the same, 0, 1, 1, 1, 0, minus 2, and then minus 2, 1, minus 1. Now, because the question doesn't want actually us to go any further, find a matrix P such that P inverse AP is diagonal. Well, yeah, I've done it. Easy peasy. You just line up the eigenvectors. And if you were, and with this P, if you were to do P inverse times by A times by P, then you would get the diagonal matrix D, where the eigenvalues in order, which is 2 twice and then 8, because this column and this column is when lambda is 2, and this final column is when lambda is 8. But you're not actually asked any of that stuff, so it's irrelevant. So I'll just get rid of it. There you go. So hopefully you like that. Yeah, that's all I wanted to talk about. Quite difficult topics, but once you get your head around it, it's actually really easy. It's in FP2 if you want to do further pure 2, or you would see it in first year linear algebra courses for most science degrees. All right, toodaloo, bye-bye.